So we're approaching the end of chapter 18. We have seen how to calculate delta H. We kind of reminded ourselves of that. How to calculate delta S. How to calculate delta G. 3 different ways, right? One way with H and S values. One way with individual delta S and delta H values, having to calculate H and S ourselves and then plug them in. And the other one with delta G values out of the table. So there's 3 different ways to calculate that. We've also seen how delta G relates to non-standard conditions, where the equation where we had Q involved. RT times the natural log of Q term in there. And we've also seen how delta G and K are related to each other. Now we're going to do a problem where we do all of that stuff all at once. Okay, so we're going to work a problem where we calculate H, S, and G, calculate KC, calculate delta G at a set of non-standard conditions, maybe even calculate a Q in there somewhere. We'll see what we feel like, okay? But we're going to work a problem where we do a lot of that stuff, because once we know what H and S and G are, we can calculate all the others. So here's our setup. I just picked an equation. 2A goes to B plus C. And I made up some H and S values. So the row of enthalpy values going across, minus 41.7 for A, minus 32.4 for B, minus 61.2 for C. Those are in kilojoules per mole. Delta S values for A is 102, it's plus 102, plus 49.9 for B, and plus 24.2 for C. Those are all in joules per mole Kelvin. So I'm going to break this video up into 2 chunks. It's easier to load into YouTube, and it's easier for you guys to watch instead of watching one big long problem. Break it up a little bit. So we're going to work the first part here where we calculate delta H for the reaction, then delta S, and then delta G for the reaction, and KC. Then we'll pause the video, set up a new one where we do some of the non-standard condition stuff. And so for this one, we're going to calculate delta H at standard conditions. And we use our first row of information, right? So we plug all of our stuff in. It'll be 1 times minus 32.4 plus 1 times minus 61.2, and then minus the quantity 2 times 41.7. So we type that through. Minus 32.4 minus 61.2. There should be a minus sign on the 41.7. So plus 2 times 41.7. 32.4 minus 61.2 plus 2 times 41.7 minus 10.2 kilojoules per mole. That's delta H at standard conditions. Then we do delta S. So step 2, calculate standard entropy change. Same setup, different row of numbers. Okay? So we have 1 times 49.9 plus 1 times 24.2, all of that minus 2 times 102. So 49.9 plus 24.2 minus 2 times 102, minus 129.9. That's joules per mole Kelvin. And in case we need it, which we will here in a second because we're going to calculate delta G, that is it's minus 0.1299 kilojoules per mole Kelvin. Then calculate delta G at standard conditions. Delta G is delta H minus T delta S. T is 298 at standard conditions, right? So we have everything we need. So we have minus 10.2 kilojoules per mole minus 298 K times minus 0.1299 kilojoules per mole Kelvin. And we run that through. 10.2, flip the sign. These negatives here cancel, so this becomes plus 298 times 0.1299. I get 28.51 kilojoules per mole. That would also mean non-spontaneous, right? Because delta G is positive. So at standard conditions, this is a non-spontaneous reaction. All right, next up we're going to calculate K. So calculate Kc. Kc was equal to e to the power of minus delta G over RT. So that's e to the power of minus delta G was plus 28.51 kilojoules per mole. This negative stays because it's part of the problem, right? It's part of the formula. I'm going to change delta G to joules per mole. 28,510 joules per mole. That way my R units work out. 8.314 joules per mole Kelvin times 298K. Again, on this setup, I changed this number up here, the 28.5 kilojoules per mole, my delta G 0. I changed it to joules so that my units worked out on the R down below. This negative stays because it's part of the formula. I'm not flipping the sign on this. It's part of the formula. All right, so Kc, I'll show my intermediate answer again. 28510, change the sign because the negative out front, divided by 8.314, divided by 298. So it's e to the minus 11.51. Second function, natural log of what's on our screen. Convert to scientific notation, 1.01 times 10 to the minus fifth. We should expect a small k value because we had a positive delta G. All right, I'm going to do the rest in a new video, but we're going to use the same equation. 2a goes to b plus c with the same h, s, and delta G values. Okay? Hang on just a second.